Is there something bigger than infinity? Let's consider. Hello philosophers, I'm Chico. Welcome to the Philosopher Show, where we consider the greatest questions of human history. Now, in a previous video in this playlist, we looked at Hilbert's Hotel, and we discovered something very bizarre. With infinite many hotel rooms that are all occupied, you can actually add an infinite number of guests. The trick was just to pair up the natural numbers 1, 2, 3, 4, 5 with the even numbers 2, 4, 6, 8, 10. And since they're both infinites, they should match up perfectly. Now, the technical word for this is countably infinite. A set is countably infinite if you can list its members in a sequence so that each number gets a natural number as its label. Every member gets a turn, none are left out. So for example, we could say in the even numbers 2, 4, 6, 8, the 2 is the first term in the even numbers, so we'll assign that 1 for the first term. The 4 is the second term in that sequence, so we'll assign that 2 for the second term. The 6 is the third term, so that's 3, etc., etc. So here's the question that we left hanging. Is every infinite set countable? Can you always make a list? Or are some infinite collections so vast that no list, no matter how clever, could capture them all? In 1891, a German mathematician, Georg Cantor, answered this question and shook the foundations of mathematics. Let's focus on a specific set. All the real numbers between 0 and 1. And for real numbers, we mean basically non-imaginary numbers. No square root of -2 or anything like that. So basically all the decimals you can write between 0 and 1. Some are simple, like 0.5 or 0.25. Some are rational with repeating numbers like 1/3, which equals 0.33333 and just keeps repeating. And some are irrational. And this would be weird numbers like pi or Euler's number, and the square root of non-perfect squares like square root of 2. Here's the question. Can you list them all? Can you write them in a sequence, first, second, third, like we did for the even numbers, so that every real number between 0 and 1 appears on this list? Now, your instinct might say yes, but Cantor proved that you cannot. And his proof is so simple it fits on a napkin. Here's how it works. Suppose someone claims to have a list of all the real numbers between 0 and 1. Their list might look something like this. Notice I've assigned each number one of the natural numbers. And assuming that this person is right, then we obviously would go past 6 and just keep writing these numbers. And we would go on forever. Now, it doesn't matter what the list looks like. It doesn't matter that I chose the specific list that we have here. Cantor will show that no matter what list you give him, he can find a real number that is not on it. Here's the trick. Go down the diagonal. Start with the first digit of the first number, the second digit of the second number, the third digit of the third number, so on and so forth. Now, build a new number by changing each one of those digits. Add 1 to each digit. So if the digit was 5, now change it to 6. If the digit was a 4, change it to a 5. Whatever the digit is, just add 1. And if you have a 9, just go back to 0. Now, this new number that we just made is not on the original list. It can't be. It differs from the first number in the first decimal place. It differs from the second number in the second decimal place. From the third number in the third decimal place. And for every number on our list, our new number disagrees with that number in at least one position, namely the position we chose when we made the diagonal. So our new number is not equal to any number on the original list. But we assumed that the list was complete. Contradiction. Therefore, no list of real numbers between 0 and 1 can ever be complete. The real numbers are uncountable. And that means that there are, in a precise mathematical sense, more real numbers than natural numbers. But that's pretty weird. Both sets are infinite, right? The 1, 2, 3, 4, 5, the natural numbers, that's an infinite set. And also all of these numbers that we can make between 0 and 1, that's an infinite set. But strictly speaking, the second infinity is larger than the first infinity. And it's not a metaphor, it's not some hand waving, this was a proof. No matter how you try to pair up the natural numbers with the real numbers, you always end up with more real numbers. Now, Cantor called the size of infinity of the natural numbers Aleph null, and that would be the Hebrew letter Aleph and a subscript 0. And he said, this is the smallest infinity. The size of the real numbers is strictly larger. Cantor called it the power of the continuum. And it doesn't stop there. Cantor proved for any infinite set, you can construct a larger set by taking its power set, basically the set of all its subsets. So there is no largest infinity. the Tower of Infinities goes on forever. Now, you might think that the mathematical world would celebrate his discovery. Some did. In fact, David Hilbert, who gave us Hilbert's Hotel, said that no one shall expel us from the paradise Cantor has created. But others were horrified. For example, Leopold Kronecker, one of the most powerful mathematicians in Cantor's time, called him a corrupter of the youth and actively worked to block his career. Kronecker thought that mathematicians should only be working with things that could be constructed with a finite number of steps. Infinite sets, in his view, were not real mathematics. Henri Poincare called set theory a disease, and he thought mathematicians would eventually recover from it. In the 1900s, Dutch mathematician L.E.J. Brouwer founded a school called intuitionism that challenged the very logic underneath Cantor's proof. He basically rejected the law of excluded middle for infinite sets. And the law of excluded middle says that for any proposition P is either true or not true, there is no third alternative, which is pretty obvious. But Brouwer argued that for infinite sets, you can't say that a property either holds or does not hold unless you can actually construct a witness. You can't say, for example, that there is a natural number with a property X, or there is not, if you haven't checked and cannot check them all. Now, this matters for Cantor because Cantor's proof was through contradiction. It assumes a complete list and then derives the contradiction from there. The final step, which says that with our complete list, we derive an absurdity, so that the opposite must be true. It must be an incomplete list. That relies on the law of excluded middle. Intuitionist mathematics doesn't deny that the reals behave differently than the naturals, but refuses to admit that there are different sizes of infinity as completed sets. All you've proved, they might say, is that certain pairing procedures fail. The attempt to pair the natural numbers with the real numbers. Not that there's some kind of Platonic object, the uncountable, that exists out there. Perhaps the most philosophically radical critique came from Ludwig Wittgenstein, one of the most important philosophers in the 20th century. Now, he didn't reject the logic of the diagonal argument. He rejected its interpretation. Here is his challenge. What does the word bigger even mean? Well, we say that there are more real numbers than natural numbers. We are borrowing a word from everyday life. There are more apples in this basket than there are apples in that one. There are more people in this room than there are chairs. In those cases, the word more has a clear, concrete meaning. You try to pair them up one to one, and some are left over. You can see the extras sitting there. But Cantor's proof doesn't show that there are some reals that are left over, the way that 3 apples would be left over if you had 10 apples in 7 baskets. It shows that any rule for pairing real numbers with natural numbers can be defeated by a specific diagonal construction. Now, that's a fact about rules and constructions. Wittgenstein says that we've been seduced by a metaphor. We took this word bigger, which works perfectly fine when we're talking about completed finite groups. And then we imported that into the concept of infinity, where it no longer carries the same meaning. Then we treated the metaphor as if it were a discovery. We said, we've discovered that some infinites are bigger than others. But what we actually discovered is that a certain diagonal procedure always produces a number that's not on a given list. That's a theorem about a construction technique. It's not a revelation about 2 ghostly infinities sitting side by side in Plato's heaven. Here's an analogy. Suppose somebody told you, I've discovered that some dreams are heavier than others. You would immediately object, dreams don't have weight. The term heavier simply doesn't apply to dreams, no matter how vivid or intense they are. You're misusing the word. Wittgenstein is making an analogous point about infinity. The term bigger doesn't apply to infinite collections like it does to finite ones. Cantor defined a technical notion of bigger, namely the non-existence of a bijection, where a bijection is just a one-to-one pairing, right? For each natural number, you have a real number. And that technical notion is perfectly rigorous, but it only superficially resembles the ordinary use of that term bigger. And when mathematicians describe one infinity as bigger than the other, they're smuggling in that original sense that we have. Finally, we have a critique from much older roots. We've seen already that Aristotle distinguishes between potential and actual infinities. You can always count one more number, divide a line one more time, and add one more guess to Hilbert's Hotel. But you never finish. The sequence never becomes a completed whole. An actual infinity, by contrast, would be a completed, simultaneously existing, infinite collection. So all the natural numbers actually gathered up. Aristotle held that only a potential infinity is real. And Thomas Aquinas after him argued that an actually existing multitude must be a determinate multitude. It must be some specific number. But an infinite multitude would be a multitude that is not a specific number. It would be a quantity that is by definition not a quantity. And that's incoherent. So philosophers of this bent would have a number of objections. First, they would question the very first move. Cantor begins by considering the set of all real numbers between 0 and 1 as a complete whole. But does this set actually exist? A Thomist would say no. You could always write down another decimal. The decimals are potentially infinite. But potentially infinite means that they're not all there at once. If the collection is never completed, you can't treat it as a single object and then start asking about its size. Second, the entire framework of transfinite cardinals assumes that infinite quantities are genuine quantities. Aleph null is supposed to be a number, namely the number of all natural numbers. But for a Thomist, infinity is not a number. It's a privation. It means not finished, not complete, not bounded, lacking a limit. Calling something an infinite number would be a contradiction in terms, because number implies determinacy, and infinite is a denial of determinacy. Third, there is a very interesting historical footnote here. So Cantor was a devout Lutheran, but he had serious Catholic connections, and he wanted to make sure that his transfinite numbers did not contradict with the Catholic teaching of the infinity of God. Not that the Lutherans don't believe that God is infinite, but this was specifically the historical setting. So Cantor made a careful distinction between the absolute infinite, which he identified with God, and the transfinite, which would be mathematical infinites like Aleph null and Aleph 1. And he said that God is unlimited in every way, whereas the transfinite numbers are only unlimited in this mathematical way. Now, for Aquinas, God's infinity is not a matter of quantity at all. God is infinite because he is pure act, unlimited perfection, not because he's a very large number. But created things are finite by nature. They have limits, boundaries, determinate natures. Now, Cantor tried to find like a middle ground between the two, and the Thomists would just say that doesn't exist. Things are either finite or they're God. Here's one of the biggest open questions Cantor left behind. If Aleph null, the size of the natural numbers, is smaller than the continuum, the size of the real numbers, is there anything in between? Is there an infinity that's bigger than the naturals but smaller than the reals? Cantor believed that the answer was no. He called this the continuum hypothesis. The continuum is the very next infinity after Aleph null, with nothing in between. He spent years trying to prove it, but he never could. In the 20th century, Kurt Gödel showed that the continuum hypothesis could not be disproved from the standard axioms of mathematics. Then Paul Cohen showed that it can't be proved from those axioms either. It is independent. So in other words, the standard rules of mathematics aren't powerful enough to answer the question one way or the other, which is crazy. It's a straightforward question about the size of infinites, and mathematics just can't answer the question. And it's not because we're not smart enough. It's because the axioms we use to do mathematics leave the question open. So Cantor cracked open the door to a world most people never knew existed. Infinity as not just one thing. Infinity as a landscape, with peaks beyond peaks. And at the very foundations of this landscape, there are questions that even our most powerful tools cannot resolve. But as we've seen today, not everybody accepts this landscape. The intuitionists question the logic. Wittgenstein questions the language. The Thomists question the metaphysics. And whether or not you stand in Cantor's paradise, the questions are fascinating. Next time, we're going to take everything that we've learned so far in this playlist and ask one of the most debated questions in philosophy and cosmology. Can the past be infinite? Has time been going on forever? Or must there have been a beginning? The answer has implications for physics, for philosophy, and for the question of God. You don't want to miss it. And as I like to say, the best philosophy happens in dialogue. So please let me know what you think in the comments. Also, don't forget to like, subscribe, and hit the notification bell. And I'll see you in the next video. Adios.